All right. So later on today, I will upload the recording to YouTube. And then I'll send out an email to everyone so that you'll get the link to the review. So that way, if you guys want to look over anything, you'll be able to do that. And likewise, those who did not attend the review, they would have access to the recording as well. All right. Now, in the email invitation that I sent out, I attached a PDF with a whole bunch of questions on it. And as I said, I'm planning on just working through some of those questions during this review. I'm going to kind of cherry pick which ones from each part. But if you guys have any questions that you want to see me work on in particular, you can post that in the chat. All right. So the audio and video is turned off for you guys because if there's too many people trying to talk, that might be difficult. So if you want to communicate with me, please use the chat instead. You can ask me at any time if you have a question, just post it in the chat. And I guess that's about it. So I'm going to go ahead and get started. So I'm looking at the questions that I sent to all of you, and I'm going to pick a few problems in part 1 to work on. So part 1 was just computing some derivatives. All right, so I'm just going to pick some of these problems to work on. I'll start with problem number 2. Okay. So in problem number 2, we're given the function f of x, which is equal to 5 times the cube root of x squared minus 4 square root of x, and plus 3 over x. We want to find the derivative of this function. All right, so in order to do that, what you first have to do is you're going to have to rewrite this. And so as a reminder, whenever you have the nth root of something, you can rewrite that as an exponent by raising it to the power of 1 over n. And then likewise, when you have something in the denominator, remember that you can rewrite that with a negative exponent as x to the negative n. All right, so in this problem, what we want to do first is rewrite our function. So we can rewrite it as 5, and then the cube root of x squared is the same as x squared to the power of 1/3. Likewise, the square root of x would be the same as x to a power of 1/2. And then 3 over x would be the same as 3 times x to a power of -1. And I'll just do one more thing is here, if I have x squared all to the 1/3, I can combine them by multiplying the exponents to get 5x to the 2/3, and then minus 4x to the 1/2, and then plus 3x to the -1. All right, so any questions about that so far? All right, so I'll be regularly asking you guys as I work on my examples if you guys understand it. Again, if anytime you have a question about something, you can just post it into the chat. All right, now that we've written our function in this form, now we can easily compute its derivative by using the power rule. So the power rule, we're going to bring the 2/3 out front. So multiplying with the 5 will give me 10/3. And then we decrease the exponent by 1. So 2/3 minus 1 will be minus 1/3. Likewise here, bring the 1/2 out front. 4 times a half is 2. And then decrease the exponent by 1. And finally, again over here, bring the -1 out front and decrease the exponent by 1. And then this would give us our final answer for the derivative. All right, any questions about that one? All right, so I'll do another problem next. Number 3 and 4 are pretty similar. I'll take a look at number 3. Okay, so next we have the function f of x. And so it's x squared minus 3x plus 1 to the 5th power. So in order to find the derivative of this function, we're going to need to use the chain rule. And so I'll kind of remind you guys how it works for functions like this. If you're trying to compute the derivative of something being raised power, so the general rule is you bring the exponent out front, you decrease it by 1. All right, but from the chain rule, you also need to multiply by the derivative of whatever was inside being raised to the power. Yeah, so I'm going to post this recording to YouTube later today. Once this review finishes, it might take about an hour or so before it becomes available for me to download. Then it might take a little while to upload it to YouTube, but it should be up by later tonight though, for sure. All right, so in this case, if I try to apply this rule to this problem to get the derivative, so I'll bring the exponent out front, decrease it by 1. But now I've got a chain rule which tells me I got to multiply by the derivative of the inside. And so here the derivative of the inside is going to be 2x minus 3. All right, and so then this would be our final answer for the derivative. All right, any questions about that? All right, cool. For this problem, I would say not really. That's about as simplified as you can make it, at least in my opinion. But also for the instructions for this part, I did write down the instructions that you don't need to simplify. Okay. All right, let's take a look at more problems. So I'll go to number 5 next. Number 5 from part 1, where we've got the function f of x, which is equal to 3 e to the x squared minus x. All right. So to get the derivative of something like this, where you've got e raised to some power. So the general rule for a derivative of an exponential is to copy it down and then to multiply by the derivative of the exponent. So applying that to this problem, the derivative of f, I'm going to just copy down my function. And then the chain rule tells me that I also need to multiply this by the derivative of the exponent. So derivative of x squared minus x will be 2x minus 1. And then we can leave this as our final answer for the derivative. All right. Okay. I'll also take a look at problem number 6 right now. All right, so for this one, we've got f of x equals 2, and then we've got a natural log of 2x squared minus 3x plus 1. Okay. So then I'll remind everyone what the rule is for computing derivatives of natural logs. So whatever you have inside the natural log, derivative is going to be 1 over the inside. And then the chain rule says you have to multiply by the derivative of the inside. And so if you want to simplify this by multiplying the derivative of u into the numerator, so you can also write it as u prime over u. Okay, so let's try to apply that rule to this example. All right, so this 2, I'm going to just bring it down, and then for the derivative of the natural log, we're going to put the inside into the denominator. Okay. All right, but again, the chain rule says we have to multiply by the derivative of the inside. So then looking at the inside, the derivative is going to be 4x minus 3. So I'll put that up top. And then that would be a good place for our final answer. All right, so any questions about any of these examples so far? Would we get the same answer if we expanded? So you would get an equivalent answer. It might look different, but it should be equivalent. So you're talking about, I think, if you were to maybe factor the inside first and then use properties of natural log. Is that right? Yeah, so I wouldn't worry too much about that. At least not for this problem. Later on, I have a problem where you will want to expand it, and so we'll get to that in just a couple of questions, okay? All right. Okay, so that was number 6 from part 1 of the problem sheet that I emailed all of you. Okay, so next, let's take a look at, I'll go to problem number, sure, let's do problem number 9 right now. Okay, so I've got f of x equals 5 e to the x squared minus 1. And then that's times a natural log of x squared plus x plus 1. All right. So in order to get the derivative of this, we would have to use the product rule. And so I'll write down what the product rule is just to remind everyone. And I guess everyone remembers it a little bit differently, but the way that I remember the product rule, so UV prime is U prime V, and plus u v prime, okay? All right, so that's how I remember it, at least. Okay, so then in our problem, let's just pick one factor to be u and one factor to be v. And what I'm going to do is I'm just going to compute u prime and v prime. Okay, so first getting u prime. So remember, to get the derivative of an exponential, we're just going to copy it down. And then after that, you have to multiply by the derivative of the exponent. And here, I think it's worth simplifying. So we'll write it as 10x, and then e to the x squared minus 1. And then for derivative of natural log, so remember, it's the inside goes to the denominator. And then you want the derivative of the inside in the numerator. So here, derivative would be 2x plus 1. Right, so that gets us v prime. So then once you have your u, v, u prime, and v prime, you can plug it into the product rule. So now getting the derivative of f. So according to the formula, it's u prime. So I'm going to copy down u prime. Okay. And then times v, so times the natural log. And then we've got plus u, which was 5e to the x squared minus 1. And then times v prime. So v prime we have is 2x plus 1 over x squared plus x plus 1. And since the problem says we don't need to simplify, then I will leave my answer as this. All right. Any questions about that? It depends. So for me, for this first part, I was primarily focused on just like refreshing everyone's memory on some of the rules regarding how to take derivatives. And I wasn't too interested in seeing you guys simplify it or having to simplify it for the review. So that's why I put that down in the instructions. I know in one of your homework assignments, you had something similar where you were just computing derivatives, but you were asked or told that you didn't have to simplify. So I think it'll just depend on your instructions. I think a good tip is if the problem only asks for a derivative and nothing else, it's probably okay to not simplify, or at least not simplify that much, because you're not going to do anything else with it. But if the problem involves having to do more, then you'll definitely want to simplify, because that will probably make the next part of the problem that you have to do easier. Okay? All right, anything else? Okay, so let's go on to another problem. So I'll take a look at number 10. All right, so here our function f of x, it's 3x cubed minus x squared plus x, and it's all over 4x squared plus 3. Okay, so to take the derivative of something like this, you would need to use the quotient rule. So here I'll write down the quotient rule. And again, this is the way that I remember it. So u over v prime, it's u prime v minus u v prime and over v squared, okay? So it kind of helps for me that at least with the way that I remember it, the numerator of the quotient rule is basically the same as the product rule, except it's minus instead of plus. So thinking of it like that kind of helps me to remember it. Okay. All right, so then u is going to be our numerator. V is our denominator. And again, what I'll do here is I'll just compute u prime and v prime separately. And then we'll put it all together at the end for the derivative of f. So in this case, u prime would be, let's see here, 9x squared minus 2x plus 1. Here, v prime is just going to be 8x. So now we can just plug all of that into the quotient rule. So f prime of x is going to be, so it's u prime times v. Okay, so here's u prime. And times v, which is our denominator up here. Then we're going to do minus u, which was the numerator, times v prime, so times 8x. And then that's all over the denominator squared. And so here's v, then all squared. All right, and then that will be the div. And again, I'll leave my answer in this form. All right, any questions about that? Okay, and then I'm going to take a look at number 12 now from part 1. Okay, so here we've got the function f of x equals, all right, so it's natural log of 4 e to the x squared minus 3x. And then we've got x to the 4th plus x squared plus 3 to the 10th power. And that's all over 5x cubed times the square root of x squared plus x plus 3. Yeah, I was actually thinking something similar when I was looking at it just now. Yeah, it's a lot better than I remember it being now that I'm writing it out. Okay, so when you have, or if you have a problem like this where you've got a bunch of stuff inside your natural log and you got to take the derivative, what you want to do in this problem is to apply some properties of the natural log to simplify it first before you take the derivative. Okay, so here I'll kind of remind everyone of some of the properties of the natural log. And then we'll see how to apply them in a problem like this as well. So in no particular order, When you have the natural log of a fraction, natural log of a over b, we can simplify that as the natural log of a minus the natural log of b. Likewise, when you have a product, so natural log of a times b, you can expand that as a sum, natural log of a plus the natural log of b. All right, next, when you have something in your natural log and it's being raised to a power, there's a property of natural log which allows you to take the exponent and bring it out to the front. So this would be k times the natural log of u. There's also a property involving natural log and the exponential. So when you have natural log of e to some power, the natural log and the e, they sort of cancel out, and they just leave you with whatever was in the exponent. We don't quite need it for this problem, but I'll note that if you have e to a power of natural log, the same thing kind of happens where the e and the natural log will cancel out, and it'll leave you with whatever was inside of the natural log. Okay. And then I'll mention just two more things real quickly about natural log, which we don't really need for this problem, but I think it's good to know. So it's good to know that natural log of 1 is equal to 0. And it's also good to know that natural log of e is equal to 1. Okay? All right, so then with those properties, let's see how to use them to get the derivative of our function. All right. So first, I want to use the first and second properties to expand this out. Okay. All right, so I guess the quick way to do this would be, okay, so here in the numerator, you can think of it as having three things multiplying each other. We've got 4 times the exponential, and then times all of this being raised to a power of 10. So when I have things being multiplied like that, I can split them apart by doing a sum of the natural logs. So in the numerator, since I have those three terms, I can break it up as a sum of 3 natural logs. I'll start with natural log of 4, then I'll do plus natural log of the exponential, then I'll do plus natural log of, let's see here, I'll write it as this, so x to the 4th plus x squared plus 3 to the 10th power, and then close parentheses. Okay, so I get that from applying the second property to the numerator. And then for things in the denominator, by this first property here, things in the denominator I want to subtract. Okay, so I've got a 5 times x cubed and times the square root. So I'm going to subtract natural log of each of those terms. So minus natural log of 5, minus natural log of x cubed, and then we have minus natural log of the square root. All right, so first I'll stop there and I'll just ask you guys if you had any questions about how I did that first part. Okay, all right, good. So that makes our problem much easier because now we have a lot less inside each of the natural logs. Okay, very good, thank you. All right, so before we take the derivative, we want to try to simplify a little bit more by applying some more of the properties of the natural log. Yep, so I applied the first two properties. I did start with the second one, and then I kind of did the first one as well. I kind of think of it as applying both at the same time, though. All right, so then looking at everything that we have right now, we notice that for the second term, we got natural log of e to a power. So we can apply this last property, which says that the natural log of the e will cancel each other out. So if we cancel the natural log and the e, we just have x squared minus 3x remaining. So let me take a look at this. Yeah, it is being recorded and it'll be up on YouTube later tonight. And I'll send everyone a link once I manage to upload it. All right. Let's see here. Next, for this term, we can apply the third property. Since we have something being raised to a power on the inside, we can bring the power out to the front. So we'll get 10, and then natural log x to the fourth plus x squared plus 3. We've got minus natural log of 5. Okay, over here, we can also bring the power out to the front and write it as minus 3 natural log of x. And then finally, for this last term, keeping in mind how a square root is raising everything to a 1/2 power. That means we can bring that 1/2 power out to the front. Again, using that third property. And then that just leaves us with x squared plus x plus 3 on the inside. All right, so again, I'll pause there and I'll ask if you had any questions about anything from that. Okay. Now at this point, we can't really do anything else. So we don't have any properties of natural log which apply to anything like this or like this. So since we can't do anything else, now would be a good time to start trying to get the derivative of f. Okay. So first, here, natural log of 4 is just a constant. There are no x's in it. And remember that the derivative of a constant is just 0. So I'll write 0 for now. And then here, derivative of x squared minus 3x would be 2x minus 3. Okay. All right, so next on this term, so I'll copy down the 10 first, and then remember to get the derivative of natural log, take the inside and put it in the denominator. and then multiplied by the derivative of the inside. So in this case, derivative of the inside would be 4x cubed, and then plus 2x. Okay. Over here for the natural log of 5, again, the derivative is just going to be 0 because it's a constant. Derivative of natural log of x is just 1 over x. And then finally, for this last one, we've got the 1/2, so I'll put the 2 in the denominator. And then for the derivative of the natural log, so take the inside, we'll put it in the denominator. And then we need the derivative of the inside in the numerator. So derivative of the inside would be 2x plus 1. Okay. And of course, the zeros, we can drop them, so I'm just going to get rid of them. All right. So then with that, this would be our final answer for the derivative of f. All right, any questions about that? All right, good. So in that case, let's maybe look at part 2. And so in part 2, it's finding the critical points and then using the second derivative test to determine if they are like relative maxima or relative minima. So there's 3 questions in part 2. Do you guys have any preference maybe for which question I do? If not, I'll probably just pick one of them to work on. All right, so it looks like number 2 will be the winner. All right, so the questions when I sent out the email inviting everyone to the exam review, I attached a PDF of questions. All right, so yeah, let's take a look at problem number 2 from part 2. Okay. All right, so the function that we have, f of x, is 2e to a power of x to the 4th minus 8x squared plus 16. And again, the instructions are to find the critical points and then use the second derivative test to find the relative extrema. Okay. All right, so before we work through the problem, I'll just mention what the second derivative test says. Okay, so suppose that we have a critical point. I'll call the critical point C. Yeah, so we suppose it's a critical point where the derivative of f was equal to 0. Okay, so as you guys should know that if you have a critical point, it could be a relative maximum or a relative minimum. So in order to test if it is a max or a min, the second derivative test says to look at the second derivative, evaluate it at the critical point, and if the second derivative is positive at the critical point, then f will have a relative minimum at this critical point. And then if the second derivative at the critical point was negative instead, then you'd get the reverse, and that f would have a relative maximum at the critical point. Okay? All right, so that was the second derivative test. All right, so then looking at the problem that we have right now, first we want to find the critical point. So we're going to compute the derivative, and then we're going to set it equal to 0. All right, so remember that for the derivative of an exponential, first is we copy it down. And then the chain rule tells us to also multiply by the derivative of the inside, or in this case, derivative of the exponent. So here, derivative of the exponent is going to be 4x cubed minus 16x. Okay? All right. And then since we're looking for critical points, we want to set that equal to 0, and then try to solve for x. Okay. Now, when you have something like this set equal to 0, and you're trying to solve for x, you can ignore the exponential entirely. The reason why you can ignore it is because exponentials can never be equal to 0. So what that means is the only way for everything to be 0 is for this part to be 0 instead. So therefore, I'm just going to take that part, I'm going to bring it down, and just set this part equal to 0. And we'll solve for x from that to get the critical points. So to solve for x, we can factor out a 4 and an x from both terms. That will leave us with an x squared from the first term, and it will leave us with a minus 4 in the second term. And from here, let's see here, x squared minus 4, I suppose we can factor that a bit more as x minus 2 times x plus 2. And then from here, we see that we have 3 critical points. So when x is 0, that is 1 critical point. Then when x is 2, and when x is negative 2 as well. Okay, so I'll pause there, and I'll just ask if anyone has any questions about anything so far. All right. You guys don't have to be shy about posting in the chat. In case you were worried, when we upload the video to YouTube, the chat won't be visible. So no one's going to see you posting anything once we upload the recording. All right. So if there are no questions, we've got all of our critical points. So now what we want to do is apply the second derivative test. Thank you. All right. So in order to apply the second derivative test, we do need to get the second derivative first. So let's work on that next. Okay. And just maybe to make it easier to see, I'm just going to copy down the first derivative. All right, so we need the second derivative. So in order to get the derivative of everything here, it is a product, so we're going to need to use the product rule for this one, okay? All right, so again, I'll write out the product rule for reference. All right. And just as before, I'm going to compute u prime and v prime separately, and then I'm going to put everything into the product rule to get the second derivative. So for u prime, when we get the derivative of the exponential, so remember the rule for that is to just copy it down. And then the chain rule tells us to multiply by the derivative of the exponent. So derivative of the exponent, that's 4x cubed minus 16x. Right. So it does happen to just actually be the same as f prime. But if we also compute v prime, that's going to be, see here, derivative is 12x squared minus 16. Okay. And then now that we have u, v, u prime, and v prime, we'll put everything into the product rule to get the second derivative. Okay, so we're going to take u prime So u prime is all of this. All right. And then we've got times v, so times another 4x cubed minus 16x. So when I multiply both of them together, I'm just going to get 4x cubed minus 16x squared. So I'll go ahead and write it like that to make it a little bit easier. And then we also have plus u. So here I'm going to copy down u. All right, and then times v prime. So we're going to times 12x squared minus 16. All right, so then any questions about any of that before I go on? Okay. Now here it's maybe not super important, but I think it would be nice to simplify this just a little bit. So both terms have the exponential in common. They also have a 2 in common. So I think it would be nice to at least factor out the 2 and the exponential from both terms. That will leave me with 4x cubed minus 16x squared. And then we've got plus 12x squared minus 16. And we could do a bit more on the side to try to simplify it some more. But rather than doing that, I'm going to do something else now. All right. So we got the second derivative, and remember that we're trying to apply the second derivative test. So for that, what we want to take our critical points and plug them into the second derivative to see if it turns out to be positive or negative. And then from that, we can determine if we have a relative min or a relative max. Okay, so we want to plug each of our critical points into the second derivative. I'm just going to start with x equals 0 first. So if we plug in 0 for x into the derivative, okay, so we're going to get 2e to the 16. And the brackets we're going to get, so here, this will all be 0 when we plug in 0 for x. And we're just going to get negative 16 inside the brackets in the end. All right. Okay, so exponential is always positive. So we've got positive times a negative. So that means ultimately the answer will be negative, okay? All right, so because we got a negative from the second derivative, that tells us that our function will have a relative maximum. At here at the critical point at x equals 0. And if they ask you for the value of the relative maximum, to get the value of it, you want to plug your x value into the original function. So let's see here. What was the original function? I'll write it up here for reference. So f of x, the original, was 2e x to the fourth minus 8x squared plus 16. Okay, so if we plug in 0 for x, we're going to get 2e to the 16. Okay. So when you're looking at the question, maybe pay attention to the wording. If they're just wondering where the relative max and min are, then to me, that would just need the x value to answer the question. If they want the value of the relative max or the relative min, then to me, you'd want to plug your x value into the function to get the actual value of it. If you're not sure if they just want the x or also the value of your function, to me, it never hurts to give both of them in your answer. So to me, that's kind of the safest thing to do. If you're a little bit unclear about the instructions, just always provide both of them as an answer, okay? All right, so we checked the first critical point. We got to check the remaining ones. So Next, let's plug 2 into the second derivative. Okay, here it is. Okay, so when you plug in 2 for x, you're going to get 2. You're going to have something in the exponent, which is not too important. Now looking inside the brackets, if you plug in 2 for x, so here you're going to get 4 times 2 cubed. So that's going to be 4 times 8. And then you're going to get minus 16 times plug in 2 for x squared. And then you've got plus 12 times 2 squared minus 16. Now over here, you actually get 32 minus 32, meaning this whole thing just becomes 0. And exponentials are always positive. So you don't even need to worry about what the exponent actually is. So that saves you a little bit of time. You don't need to compute it. What we have remaining in the brackets is going to be 12 times 4. So it's 48 minus 16. So altogether, it's going to be positive inside the brackets. Okay, so then multiplying two positives will give you a positive answer in the end. So therefore, according to the second derivative test, since the second derivative is positive, your function has a relative minimum. So we'll say f has a relative minimum at x equals 2. And if you want, you can plug 2 into the original function to get the value of the relative minimum. So if you plug in 2 for x into the original function, you'll get 2e to the, see here, 16 minus 32, 16. Oh, you'll get 2e to the 0, which will just be 2 times 1, so it'll just be equal to 2. Okay, so that's pretty simple. And then finally, we have to plug in the last critical point, x equals negative 2. Okay, so finally, let's check when x is negative 2. We'll plug that into the second derivative. Okay, so again, over here, plugging in negative 2, you're going to get 2e to something. Again, you don't need to worry about the actual exponent because you know that exponentials will always be positive. Okay, now let's see. If we plug in negative 2 for x, okay, so negative 2 cubed will be negative 8. We get minus 16 times negative 2. Okay. Then we'll get plus 12 times negative 2 squared and minus 16. So now here in the parentheses, you actually get negative 32. This will be plus 32. So actually, again, this part becomes 0. Here, when you square, you're going to get 12 times 4. So again, it's 48 minus 16, meaning again, it is all positive. All right, so then again, since the second derivative was positive at the critical point, we can say that f has a relative minimum according to the second derivative test. And then finally, again, plug it into the original function if you want to get the value. I think, again, you actually get 2e to the 0. So you'll get that it's equal to 2. All right, so any questions about any of that? All right. If nothing else, then I'll take a look at some questions in part 3 now. Okay, so part 3 was just evaluating some limits. Let's see here. So I'll start by looking at problem number 2, okay? So part 3 is evaluating some limits. Here the instructions are to not use L'Hopital's rule. So we're going to be evaluating these limits without using L'Hopital's rule. All right, so here's the limit in question number 2. So it's the square root of x squared minus 3x plus 6, and then minus 4, and then that's all over x squared minus 4. All right, now when you are trying to evaluate limits, I do recommend always plugging in whatever x is approaching, plugging that in for x into your limit, just to see what it gives you. So if we plug in -2 for x, we're going to get inside the square root. -2 squared will be positive 4. Minus 3 times -2. So double negative would be plus 6. Oh, did I miss this one? Let's see here. 4 minus 2. Oh, no. Okay, because I want to, yeah. And then I want to do plus 6. Okay. And then minus 4. And then that's all over. And again, if I plug in -2 for x, it's going to be 4 minus 4. And if you check right now, we see that we get 0 in the denominator. Here, we get the square root of 16, which is 4. And 4 minus 4 is actually 0 again. So anytime that you get 0 over 0 in a limit, that means that you have to do some extra work in order to figure out the actual answer. But if they give you a problem and you plug in your x value and you get like an actual number, like not 0 over 0, then that number would be your answer and you wouldn't have to do any additional work, okay? So I think it's always worth just double checking that you do have 0 over 0 before you start doing more stuff to your problem. Okay. Now, when you have a 0 over 0 situation with a square root in it like this, there was a standard technique for dealing with these problems. So the standard technique was to multiply the numerator and the denominator by the conjugate of whatever had the square root in it. And if you guys remember what the conjugate was, so here I'll kind of write it off to the side. But these expressions, a minus b and a plus b, these are known as conjugates. So really all you do is change the sign in the middle to get the conjugate of something. And so here I think of the square root as my a and the 4 as my b. So to get the conjugate, it's going to be a and then plus b for the conjugate. And I need to multiply both numerator and denominator by the same thing to ensure that I don't actually change my problem, okay? All right. Now, when we multiply by the conjugates, what that does for us is it simplifies. In this case, it'll simplify the numerator by getting rid of the square root. Okay. So when you try to multiply these out, so you're going to get a squared, and that gets rid of the square root. Now you're going to get plus AB minus BA. So those two terms are going to cancel out, and that always happens when you multiply by the conjugate. And then you're still going to get minus B squared. So you're going to have minus 16. All right, so that's what the numerator will simplify as. In the denominator, we're not going to multiply these out because it's not going to simplify. So for now, I'm just going to copy it down as it is. We've got x squared minus 4. And then we've got this, square root. X squared minus 3x plus 16. Plus 6. And then plus 4. No, so when you're doing this, when you multiply by the conjugates, I would multiply the conjugates together because that will simplify. I likely would not multiply the other part out because here you can kind of see you're just going to get more square roots on everything when you FOIL it out. So it's nicer if you just leave it not multiplied instead. Okay. All right, so then in the numerator, 6 minus 16 is minus 10. In the denominator, see here, I will copy it down one more time. All right. Now, we still want to do a little bit more work. So what we now want to do is try to factor in our numerator and our denominator. We need to try to cancel something out from both numerator and denominator before we can try to evaluate at x equals negative 2. So in the numerator, if we want to factor it, looks like we can factor it as x plus 2 times x minus 5 Likewise, in the denominator, x squared minus 4 we can factor as x plus 2, and then x minus 2. So that's kind of another reason why you wouldn't want to have multiplied the denominator out, because you actually want to try to factor it instead. Okay. So once you're finally able to cancel something from the numerator and denominator like that, that's when you can try to plug in x equals -2 again in order to get your answer. So plugging in -2 for x, we're going to get -7 in the numerator. Over here, we're going to get -4 times, and let's see what we get over here. So plugging in -2, you get 4 plus 6 plus 6. So it's actually a square root of 16. It's actually what we saw earlier. All right, so then that's going to be 4 plus 4 is 8, times 4 is 32. And the negatives cancel. So we've got a final answer of positive 7 over 32. All right, any questions about that? Okay. All right, now let's see here. So that depends. So in this case, we had to FOIL out the numerator. That's because the square root was in the numerator though. Whoa, okay. But if you say look at problem number 3 in my practice problem, practice problem worksheet, the square root is in the denominator. You'd multiply by the conjugate of the denominator, and you'd want to FOIL everything out that was in the denominator instead, okay? So it's not so much always the numerator as it depends on where the square root was in the problem. All right, great. Now let's see here. I see that I am not managing my time too well because I've got 45-ish minutes remaining. So let's see. I definitely want to do a bit more of the integration, I think. I feel like that's what you guys might want to see more of. So maybe I will do one more problem from part 3, and then I'll take a look at some problems in part 4, and then I'll try to get to the integration after that. So I'll ask you guys, is there a particular problem in part 3 that you would like me to work on? Number 8, all right. Does anyone have any other questions that they'd really like to see worked out? Okay, so let's try to wrap up part 3 with problem number 8 then. Yes, that is correct. Whenever you get 0 over 0, then you want to try to cancel something from the numerator and denominator, unless you're doing L'Hopital. All right. So number 8 is actually a pretty simple one, actually. All right, so it is a limit where x is approaching, in this case, negative infinity. So limits where x is approaching infinity or negative infinity often work differently from like other limits where x is just approaching a number, and you have like different techniques for how to handle it. Okay. Now, for problems involving e as x is approaching infinity or negative infinity, it's good to know some rules about how e and infinities work. So here I'm drawing a graph of the function f of x equals e to the x. And we can see a couple of things in the graph of the function. So we see that as x approaches infinity, meaning as it moves out further and further to the right. So notice that e to the x will be shooting upwards. It'll be approaching infinity. All right, so in other words, limit as x approaches infinity of e to the x is infinity. And you can remember this by simply thinking that e to the infinity equals infinity. Now, on the other hand, if you take a look at what's happening as x approaches negative infinity, meaning as it moves out further and further to the left, looking at the function e to the x, you see that it will actually approach a value of 0 as x approaches negative infinity. So a good way to remember this is to just remember that e to the negative infinity is 0. All right, so in this problem, if you just plug in negative infinity for x, so it'll be e to the minus infinity plus 3 over 0, 2 minus e to the negative infinity. Okay, and then e to the negative infinity is just 0. So you just get 3 on top and 2 on bottom, and that will be the final answer. Okay? All right, so any questions about that? All right. So I'll do 1, maybe 2 problems in part 4. Let's see. And then after that, I'll try to focus the rest of the review on the integration. Okay, so part 4 now is involving L'Hopital's rule. Let's see here. All right, so for L'Hopital's rule, let's see here. Do you guys have a preference for which problem? If not, I will pick one of them. Oh, All right, yeah, let's take a look at number 2 right now. Okay, so we've got I see. Well, okay, so in problem number 2, we have the limit as x approaches 0. And on my PDF, I see that I have e to the x plus e to the negative x over x to the 4th minus 3x cubed. plus 2x squared. However, I see that that was actually a typo. I would like to have minus instead of plus in the numerator. So let me change it to minus as I work it out during this video. All right, and let's see how this problem is going to work, all right? So first, if we plug in 0 for x, so e to the 0 is 1. So you're going to get 1 minus 1, which is 0. Here, if you plug in 0 into the denominator, you also get 0. All right. Now, for these problems, we are allowed to use L'Hopital's rule. So let me quickly mention what L'Hopital's rule says. Okay. So if you have the limit as x approaches something, so I'm just going to put a letter a there, a variable, but it could be approaching a number, or it could be approaching infinity or negative infinity. But if you got a limit like this and it gives you either 0 over 0 or an infinity over infinity, L'Hopital's rule says that you can try to evaluate the limit by instead looking at the limit of the derivative of the numerator and then over the derivative of the denominator. Okay, so since we did get 0 over 0, then we can apply L'Hopital's rule. So here I'll just make a little comment. So we're applying L'Hopital's rule right now. So we're going to have the limit as x approaches 0. Okay. Now in the numerator, when we compute the derivative, so derivative of e to the x is just itself minus, and then derivative of e to the negative x will be e to the negative x, but then times the derivative of the exponent, so times negative 1, which will make that a plus. Here it's x cubed minus 9x squared plus 4x. If we, now that we're by L'Hopital's rule, we try to plug in 0 for x once again. Here, it looks like I'm going to get 2 in the numerator, and I'm going to get 0 in the denominator, though. Okay, well, so when you get a non-zero number over 0, that's a sign that the limit does not really exist. So I think I just created a sort of bad example for this problem. I probably meant for it to be 0 over 0 twice, so that you would have to use L'Hopital's rule twice. But I must have made a mistake when I was creating the problem, okay? So I will apologize for that. Maybe take a look at another problem in part 4 if you guys want, or would you prefer me to move on to the integration? I'll let you guys decide. All right, great. Yeah, okay. So let's move on to integration. All right, great, okay. So let's see here. Maybe let's start with problem number 2. Or are you guys okay with problem number 2? All right, let's start with problem number 2 first. I assume you guys can do problem number 1. Number 2. Okay. All right, 3x minus 2 root x plus x squared e to the 3x all times x squared, and then dx. So yeah, I think that was not a good question that I created. Right. And when you get a non-zero number over 0, that means that the limit didn't exist. All right. Can you guys not see what I'm sharing right now? Did it like go away? Okay, give me 1 second, so I'll try to bring it back up then. Yeah, now, or is it still not working? Okay, cool. All right, very good. Okay, yeah, just let me know if that happens at any time, and I'll try to. All right. Okay, so in order to evaluate this integral, you want to do some simplification of what you have on the inside. So with something like this, what you can do is just simplify by dividing each term by x squared. Okay. So we can write it as 3x over x squared, and then minus 2 root x over x squared, and then plus x squared e to the 3x over x squared. All right. Okay, and then continuing to simplify each term, 3x over x squared is just 3 over x. To simplify this next term, it helps to rewrite the square root of x as x to the 1/2. So then when you're combining these together, your general rule is to subtract the exponents. So you can write this as minus 2, and then x to a power of 1/2 minus 2. And 1/2 minus 2 will be negative 3/2. Okay? On this next term, the x squareds will cancel, so it's just e to the 3x. All right. And then from here, we can now integrate each term. So the integral of 3 over x will be 3 natural log absolute value of x. And then integrating this, you'll use the power rule. So for integration, you're going to add 1 to the exponent. So it'll be x to the negative 1/2. Then you divide by the new exponent. So again, divide by negative 1/2. Okay. And then you've got, for the derivative of, or sorry, for the integral of e to the 3x, that'll be 1/3 e to the 3x. All right. This was a definite integral, so once you get all the antiderivatives, now you want to plug in your bounds and then subtract. So first plug in 4 for x. So we'll get 3 natural log of 4. Over here, let's simplify this first. So dividing by negative 1/2, you can multiply by the reciprocal. So you'd multiply by negative 2 over 1. So that'll become plus 4 if you do that. So I'll write it as plus 4 x to the minus 1/2. Okay. And then we're plugging in 4 for x. And then we'll get plus 1/3 e to the 12. And then minus what you get when you plug in 1 for x. So 3 natural log of 1. This will be plus 4, 1 to the minus 1/2. And finally, plus 1/3 e cubed. Okay, and just simplifying a little bit to get the final answer. Okay, so you got 3 natural log of 4. Now for this one over here, remember that 4 to the negative 1/2? Negative moves it into the denominator. And since it's to the half power, that's the same as square root. So then that's 4 over 2 should be equal to 2. Let's see here, we've got plus 1/3 e to the power of 12. And here, good to remember that natural log 1 is 0. And then 1 to any power is just 1. So that's going to be just minus 4. And then you're going to get minus 1/3 e cubed. Okay, and that's probably good enough place to stop. I guess you can combine 2 minus 4 to be negative 2. But aside from that, I'd probably leave my answer as it is. Okay, so we would have that for the final answer. All right, so any questions about any of that? All right, so let's see here. Okay, so let's do some more problems. I'll take a look at number 3 right now. So we've got the indefinite integral of x minus 1, and then times x squared minus 2x plus 4 to a power of 7. Okay, so in this case, this is not something that we can really try to simplify first, as we did in the in this problem where we were able to do some algebraic manipulations to simplify the inside. Here, we don't really want to do that, especially with this being raised to a power of 7. So that means that we have to either do U substitution or we have to do integration by parts. Now, I'll get to integration by parts, get to problems 8 and 9. So right now, this is a U sub problem. And when I get to the integration by parts, I'll kind of tell you guys what to look out for. Know that's going to be integrating by parts. Yeah, that would be problem number 6 would be one of those. All right. So yeah, we'll do U substitution on this one. And all right. For our choice of U, here it'll be easiest if we choose U to be x squared minus 2x plus 4. So that's going to have the effect of giving us U to a power of 7 in the integral. So it greatly simplifies what we have over here. Now next we also need to compute du. So that would be getting the derivative. So it's going to be 2x minus 2, and then dx. All right. Okay, now notice that inside our integral, we've got x minus 1 that we need to get rid of. And so to get rid of it, we'll use our du equation. And I notice that if I divide both sides by 2, we get that 1/2 du is equal to x minus 1 dx. So what that tells me is I can replace x minus 1 dx in the original integral with a 1/2 du. Now the 1/2 as a constant, I'm just going to put it out to the front. And in du, it's customary to put that at the end. All right. Now that we've managed to convert everything in terms of u and d, now we're just going to integrate this. So it's going to be 1/2 u to the 8 over 8. And then to simplify that, let's see here, 2 times 8 is 16. And for an indefinite integral, you want to sub back in for u, the original expression in terms of x. So instead of u to the 8, we're going to sub back in x squared minus 2x plus 4 for u, then to the 8, and then you got plus c. All right, any questions about that one? All right. I'll do number 4 real quickly as well. All right, let's see here. Yeah, so from this equation, what I did was I divided both sides by 2. So dividing this by 2 gave us x minus 1. And then dividing du by 2, I just wrote it as multiplying by 1/2. Okay? And then the reason why I chose to do that is because we had x minus 1 dx the integral. So I was trying to get an expression to sub in for x minus 1 dx. Okay? All right. Yeah, so I'll take a look at number 4 as well, where we've got an indefinite integral of x minus 2, then over x squared minus 4x plus 6 dx. Okay. Now again, for this problem, we can't really do much in terms of simplification with it. So we're going to do either u sub or integration by parts. And again, for a problem like this, u sub is going to be the better choice. And for a problem like this, we'll choose u to be the denominator. All right, so then here when we compute du, let's see, it's going to be 2x minus 4 dx. And so let's see, right now in the integral, we've got u in the denominator. And then I need to sub or replace x minus 2 dx with something. So I'll come back to here and I see that I can get an x minus 2 if, again, I divide both sides of this equation by 2. So divide 2 will give me x minus 2 dx. And then dividing by 2, I'll write it as multiplying by 1/2, as I did earlier. So that tells me to replace the x minus 2 dx with a 1/2, which I'll put out in the front. And then the du, which I'll put at the end, leaving us with a 1 in the numerator there. Okay. Now we just focus on evaluating this indefinite integral. So 1 over u du, the integral becomes the natural log, absolute value of u. And then finally replace u with here the original expression of x squared minus 4x plus 6. All right, any questions about that one? All right, great. So I'll take a look at number 6 now. So number 6 is a definite integral, minus 1 to 1. Okay, we've got 2x squared minus x, and then you've got e to the 4x cubed minus 3x squared and dx. Okay, so for this problem, we are going to do u substitution once again, because it's too complicated, so that we can't really do anything immediately with it. So we've got to apply one of our techniques, and we'll apply u substitution. Now, for problems involving the exponential, if you're going to do u sub, typically a good choice for u is the exponent. So we'll choose u to be 4x cubed minus 3x squared. So then, as usual, you got to compute your du. And so here the derivative is 12x squared minus 6x dx. All right. All right, so let me start by substituting some things into the integral. So we see the exponential is now just going to be an e to the u. And then we do, again, need to do something about the 2x minus, the 2x squared minus x dx. And so if we go back to our du equation, notice that if we divide this by 6, that we would get 2x squared and then minus x. So we're going to divide both sides by 6, which will leave us with 1 over 6 du. So therefore, we can replace both of these with 1/6, which I'll put out front, and then a du, which I will put at the end. Not for this one. I would say most of your problems are going to be either u sub or integration by parts, and not both. It's somewhat conceivable that you could have a question that you could solve using either method. But I would say a majority of them, like one is going to be like the right choice, if you will. Okay. And I'll get specifically to the types of integrals that involve integration by parts, especially when I get to problems 8 and 9 in this part, okay? All right. Okay, and then here, since it is a definite integral, there is one more thing that we are going to need to do. So my understanding is that whenever you guys do u sub on a definite integral, that you also need to solve for your new bounds in terms of u. So here we had the original bounds of -1 and 1 for x. So what we want to do is plug these values of x into our equation for u to get the new bounds on u. So when x is -1, plug that into here. And we're going to get u is -4 minus 3, so it would be -7. Then we also need to plug in 1 for x. So plugging in 1 for x will give us 4 minus 3 should give us 1, okay? So that means instead of x equals -1 at the bottom, we're going to do u equals -7. And then instead of x equals 1 at the top, we're going to do u equals 1 at the top, okay? All right, so at that point, integral of e to the u du is just e to the u. And now what we're going to do is just plug in our bounds of -7 and 1. So we're going to get 1/6 e to the 1 is e, and then minus e to the -7, like that, okay? So when you're doing a definite integral on u sub, if you solve for the new bounds in terms of u, then you can pretty much forget about anything that had to do with x for the remainder of the problem. So don't plug back in for u, but rather just plug in your new bounds in terms of u, and then just go from there. Okay. Yeah, so when we're doing, so there's another way that you could do the problem, and maybe it's just good to see it as well. So I've kind of been hearing that most of you seem to be doing the problem this way, where you solve for the new bounds in terms of u. Here, I'll just maybe illustrate, however, an alternative method, and maybe in case some other professors are doing it this other way instead. So the alternative method is to, let's see here, let me try to switch colors. Okay, so for the alternative method, which I'll do in green, Okay, so a couple things will change for the alternative method. You don't do this. So instead, you would just have, after doing the u sub, 1/6 integral e to the u, which you would just evaluate as just being 1/6 e to the u. But then what you want to do is switch back to x. So as usual, replace u with the original expression, 4x cubed minus 3x squared. And so if you do this where you switch back to x, then you're going to plug in -1 and +1 for x. And if you do that, you should get the same answer that we found originally, okay? So in the end, either solve for the new bounds in terms of u, and then use those new bounds when you're plugging the numbers in, or don't get the new bounds into u, but instead switch back u to x, and then use the original bounds to x, okay? I would say not really. You could, but like it might be difficult. Like in theory, you can probably force any integral problem with a u sub. However, some problems are easier to do using other methods, and so it would be best to do them using the other methods instead. Yeah, I'll definitely do an integration of parts. So I think right now what I'm gonna do is we just did number 6. So I'm also gonna do number 7, 8, and 9. Then I'll take a little bit. We'll take like a short, 3-minute break or so. I can come back and also do some problems from part 6 afterwards, even though it's going to be packed. And so if you guys will stick around, then we'll also do a couple more problems in part 6. We'll maybe try to end it around 3:30 if you want. All right. So let's go ahead and continue working on part 5. I would like to do parts 7, 8, and 9 right now. Okay, so we did number 6. Let's see here. I'll switch back to black. Yeah, the recording will be, we'll post it to YouTube, and I'll email everyone a link to it once I get it uploaded. It'll probably be later tonight. Okay, so let's see, number 7. So we've got the indefinite integral, 4 plus 2 ln bx, then over 5x dx. All right. All right, so for this problem, again, this is a good problem to do using u substitution. So real quickly, for any integral that has a natural log in it, you're always going to have to do either u sub or integration by parts, because there's nothing else you can do if there's a log in it. It's got to be one of those two. So in this problem, it's well suited for a u substitution. So let's do that. I'm going to choose u to be 4 plus 2 ln of 3x. Now, if I make that my u, when I compute du, so 4 becomes 0. Here, we get 2, and then the derivative of natural log of 3x. So remember, for natural logs, put the inside in the denominator, and then multiply by the derivative of the inside. So that's going to simplify to give us du is 2x dx. All right, so now looking inside the integral. Okay, so the numerator, we can replace it with u. Okay, so now let's see what else can we do. Okay, so I think I'll do one thing first actually, which is, let me rewrite this to make it look maybe a little bit clearer to what we're going to do. So I'm going to rewrite it as 4 plus 2 ln of 3x times 1 over 5x dx, okay? Because that way it's going to look a little bit nicer, especially when trying to figure out how to use the du equation, okay? And actually something even nicer that I can also do is, here I've got a 1/5 times 1 over x. I'm going to pull that 1/5 out to the front. So this is just me kind of cleaning these up before I do the u substitution. All right, any questions about how I did that so far? Oh, all right, 1 second. I gotta plug in my laptop before it dies on me. Let's see here. Okay. All right, so back to the problem. You could, yeah, you could. It might make it look a little bit more clear perhaps as well. And then can you explain the last part one more time? Yes, I can. Okay, so what I did was with the 1 over 5x, I pulled out the 1 over 5 to the front. So that way it would just leave me with 1 over x dx. Okay. All right. Now, if we continue with the u sub that we have going on over here, so let's see, we got the 1/5 in the front right now. We've got u, and then as for the 1 over x dx, here we got 2 over x dx. So if we multiply both sides by 1/2, it will cancel out the 2, leaving us with 1 over x dx. And so therefore, we can replace 1 over x dx with a 1/2 du. I'll put the 1/2 out front and then du at the end. Okay. All right. From there, we can write it as 1/10. And then integral of u du would be u squared over 2. So finally, we'll get, let's write it as 1/20. And then u squared, we'll replace u with 4 plus 2, ln of 3x. And then squared plus c. All right, any questions about that? Okay, all right. And now we'll take a look at number 8 and 9, which will involve integration by parts. So how did I get the 1/2? So that came from when I was messing around with the du equation. And I was trying to get 1/x dx so that I could replace 1/x dx with something. So to get a 1 over here, I needed to multiply both sides by 1/2. So the half canceled with the 2 to give us the 1/x dx. And then we managed to sub in the 1/2 du for it inside the integral. Okay? Yes. Mm-hmm. All right, good. All right, so yeah, now I want to take a look at problems involving integration by parts. Okay. So let's see here. So I think what I'll do right now is I'll do number 9 first before I go back to number 8. So here we've got the integral of x squared plus 2 times natural log of x. Okay. And I want to do number 9 first because I think it might be useful to sort of contrast this with problem number 7, which also had a natural log in it. Okay. So both of these integrals, number 7 and 9, they have natural logs in them. But we ended up doing u sub for number 7, and we're going to end up doing integration by parts on number 9. So if you're kind of wondering how to tell if there's a natural log in your integral, how to tell if you're going to do u sub or integration by parts. U sub, there's a good chance that U sub is going to work. If you got a problem looking like this, where you got an x in the denominator like that, the reason why is because if you do a U sub, you kind of know that if you do to be natural log, your du is going to have an x in the denominator, so that you might be able to get rid of that x in the denominator by using your du equation. Okay, so I would say like a rough rule that you can try to follow is there's a natural log in your integral and it's being divided by an x like this, that u sub is probably a good choice. For anything else when involving a natural log, you'll want to do integration by parts instead, okay? Any questions about that? Okay, so in that case, here is the formula for integration by parts. And then there was also like in order to do integration by parts, you got to choose something to be u and something to be dv in your integral. And I think you guys learned a little acronym to help you determine what to choose for u. So the acronym was LAE. So the U stands for, or the L stands for logs. A stands for algebraic. And the E stands for exponentials. Okay. But what this acronym tells you is that if there is a log, like a natural log in the integral, that should always be your choice for u. Next, if there are no natural logs, you should choose u to be an algebraic expression. Algebraic, you can just think involving powers of x only, no e or natural log. The fact that exponential is last means that you pretty much never choose an exponential to be u when you are doing integration by parts, okay? All right. So if I follow this rule, then I'd want to choose u to be the natural log because that has the higher priority according to this acronym. So therefore, dv is going to be x squared plus 2 dx. So then what we'll do is we need to get du by taking the derivative of u. So that's going to be 1 over x dx. We also need to calculate v, which we get by integrating dv. So the integral of x squared plus 2 dx is x cubed over 3 plus 2x. Okay? Okay, so now we're going to plug everything into our formula for integration by parts. So the integral of u dv should be equal to u Sierra times v. And then let me see what that was. Yeah, so differentiate u to get du and integrate dv to get v. Okay. So now we're using the formula over here. So it's going to be equal to u times v. So u times v. And then we're going to do minus the integral of v times du, so times 1 over x dx. All right. Now at this point, we don't need to do anything else with this over here. So I'm just going to start copying it down each time. Now, what we do need to do is we do need to integrate all of this still. But now this is something that we can integrate just using some like more basic rules. So first, we'll try to simplify by putting the 1 over x inside. So if I distribute the 1 over x, we're going to get squared over 3 now. And here it's just going to be plus 2. Okay, and so next we can integrate this. So let's see here, x squared over 2 will become x cubed over 3. And then 3 times the other 3 gives us a 9. It's going to be plus 2x. And now that I've integrated everything, because it was indefinite, I also start writing plus c. And here I don't see too much simplification you could do. So I'm going to go ahead and leave my answer in this form. Okay? All right, so any questions about that? All right, we'll do one more example, then we'll take a short break, and then I'll do a little bit from part 6, okay? Okay. And let's see, oh, before I do let's do number 8. So I'll do over here, it's the integral of x squared minus x plus 1 e to the 3x dx. And here we are going to do integration by parts, but I do want to compare and contrast questions number 6 and 8, because both 6 and 8 involve an exponential. But in 6 we did u sub, and 8 we did, and we're going to do integration by parts. So regarding integrals involving the exponential, a general rule that you can use to sort of guide you as to whether you do either u sub or integration by parts. If you're integrating a polynomial times an exponential, and let's say your exponential looks something like this, where the power of x in the exponent is only a power of 1, so no like x squared or anything higher. You'll do this integral by doing integration by parts. And then if we look at number 6 that we did a moment ago, one of the things that's different is that your exponent for e is a lot more complicated, has some higher powers of x in it as well. So if you got an exponential inside the integral, but the exponent is more complicated than just kx, so like higher powers of x, or maybe even something else, you're more than likely going to want to do u sub on this instead then, rather than doing integration by parts, okay? So this is a problem where you do u sub, and you choose u to be whatever was in the exponent of the e. Okay, so that's kind of like a rough guide for how to distinguish whether to do u sub or integration by parts if there's an exponential in the integral. All right, so any questions about that before we take a look at problem number 8? All right. Now, when you have an integral of this form where it's a polynomial times e to the kx, then there's kind of like a faster way of doing integration by parts for these types of integrals in particular. So in theory, you can do this to any integral where you're doing integration by parts, but it's only going to be most useful, I think, for integrals of this specific form, where again it's a polynomial times e to the kx. So here's how it works. You'll set up a table, and at least from what I've seen you guys doing is you're going to label one column as d for derivatives, one column as I for integrals, or integrating. And in the derivative column, you're going to put down your choice for u. And if you remember from our acronym, that we pretty much never choose exponentials for u. So therefore, we're going to choose u to be the polynomial, the algebraic expression. So then whatever your dv is, that's going to go in the integral column. And really, I guess I only care about I don't care too much about the dx for this, so I'll just do that. Okay? All right. So then what you're going to do is in the derivative column, you're just going to start taking derivatives. You keep going until you get 0. Okay? For integral column, you're going to keep integrating. So here when I integrate e to the 3x, it's going to be 1/3 e to the 3x. Integrating again gives us another 1/3, so it'll be 1/9 now. I'm going to go one more time, so we get another 1/3, so it's now 1/27. Okay? So now, with that, we'll stop once we get to the place where we got a 0 in the derivative column. And now to get the answer to our problem, we're just going to combine all of these in a certain way. So let me bring this over to here. So what we're going to do is we're going to multiply diagonally, multiplying this with that. So I'll write it as 1/3 x squared minus x plus 1 e to the 3x. And so next, we're going to do the same thing. We're going to multiply these two together. Right, but I'm going to subtract that product. So I'll write it as 1/9 2x minus 1 e to the 3x. I'm going to go one more time and multiply these together. And now I'm going to add them. So we're going to do plus 2 over 27 e to the 3x. Okay. So the rule is to sort of multiply diagonally like this. And then there's like an alternating sign pattern where you'll do plus, minus, plus, and so forth if you have to continue. So that accounts for the minus and then plus, okay? And then after that, once you've done, so there will be nothing else because you do 0 times something, which is just 0. So after you write all that down, you can just put a plus c at the end for an indefinite integral. And that gives you the value of the integral. Okay? If for a definite integral, then instead of plus c, you'd stop, and at this point, you plug in your bounds. All right. And so it may not look like it, but this is actually doing integration by parts. But we're just organizing things into the table like this, and we're making it a lot faster by doing this, okay? So any questions about that? If you wanted to simplify that, you could factor out the exponential and then try to combine like terms. For me, since I'm not really going to do anything else with the problem, I'm going to leave it as it is. All right. So in that case, we'll take a short break. Let's do maybe a 3-minute break. I'll come back and do maybe just 2 or 3 problems, I think, from part 6. And we'll try to end it there with that, okay? All right, so we'll take a 3-minute break. You guys, of course, are welcome to leave if you need to. Regardless, I'm going to be uploading the recording to YouTube, so you can always catch the last part later. Okay? So I'll be back in about 3 minutes. All right, so I'm back. Whoops. Okay. So we'll do a couple of questions from part 6. And then before that, if I'll just say, I'll make one more comment about integration by parts. So really for integration by parts, the only two types of integrals where you would do integration by parts is again where you have a polynomial times e to the kx. Or if you've got an integral involving a natural log in it, and it's not natural log, and it's not something where you've got an x underneath the natural log. Because you've got an x underneath the natural log, you can get away with doing a u sub instead of integration by parts instead. But aside from these two types of integrals, you're pretty much never going to do integration by parts on anything else. Okay? And so that's really why I only put the two examples in my review, because this is really only two types of integrals that you'll see where you'll need to do integration by parts. Okay? All right. So finally, we'll do a bit of part 6. Let's see here. For part 6, I think it'll be better to focus on the first 4 problems, finding area, because I think that's actually harder than finding volume or average value. So let's focus on just doing some area problems, and we'll finish the review with that, okay? So go ahead and start with problem number 1. Okay, so it's asking us to find the area bounded by f of x equals 2 plus e to the x. And then we also have the bounds given y 0, x equals 0, and x equals 2. Now, if it's not too difficult, I think always that just a little sketch of the region can be helpful in calculating the area. So in this case, I know the graph of e to the x. I know what that looks like. Adding 2 to it just means it gets shifted up 2 units. So it's going to look something like this. So next I'll mark here's x equals 2. X equals 0 would be here at the y-axis. And y equals 0 would be here at the x-axis, okay? So we're trying to calculate the area of this region. And what you guys have learned about definite integrals, that if you got a graph of some function over some interval AB, and you want to find the area underneath the graph and above the x-axis, you've learned that you can calculate this area just by calculating the definite integral from a to b of your function. Okay? So in our problem, that's exactly what we're trying to calculate. It's area underneath the graph of a function and above the x-axis. So that means all we have to do is integrate x going from 0 to 2. The function 2 plus x, or sorry, 2 plus e to the x, dx. Okay? From there, this is a pretty simple integral. So it's 2x plus e to the x. And then we're going to plug in our bounds of 0 and 2. Okay, so let's just finish that up. So it's 4 plus e squared. And then minus what we get when we plug in 0. So here it'll be 0 and plus e to the 0. And then e to the 0 is 1, so we can simplify it as 3 plus e squared. All right, any questions about that? All right. So yeah, number 1 is pretty simple, but let's take a look at some of the other area problems. We'll take a look at problem number 2 next. No, so you don't always have to draw the graph. I think it can be helpful as all if you do draw it, but it's not necessary at all though to draw the graph. Yes, there is. Without graphing it, there is, and so we can talk about that. Yeah, so let's take a look at problem number 2 first, and we'll get into that for each of these problems. So this time they ask for the area bounded by 2 functions. So you can see it's different from the first problem because they don't give you any bounds on x for starters. And it's also the area between 2 functions instead of what we had in the first problem where it was area between a function and the x-axis, okay? So for a problem like this, and what you'll need to do is you need to first find where these 2 graphs are going to intersect each other, because that's going to help you determine what the bounds on x are, okay? Now to find where 2 functions are intersecting each other, the way you do that is you just set them equal to each other. So take f of x, set it equal to g of x. All right, and then here, I'm going to now rearrange to try to solve for x. I'm going to move everything to one side. So let's add 2x over. And then we'll minus 7 to get minus 6 equals 0. And this we can try to factor it now. Looks like it's going to be x minus 3 times x plus 2. So that means they're intersecting at x equals negative 2 and positive 3, okay? Okay, now, so next, in order to get the area, so the sort of general rule when you're finding the area between 2 functions is to integrate the top function minus the bottom function. So what we want to determine is which of these functions is going to be on top if we were to, say, look at their graphs. So there's two methods of finding which function is on top. So one method is always to just look at the graph. For a non-graphical method, so we know the two functions intersect at -2 and 3. So what we want to do is figure out in between which function is going to be more on top and which function is going to be on the bottom, right? So to do that, just pick any point inside this interval. So I'll just pick 0 because that's a pretty nice number in between -2 and 3. And just take that number and plug it into both of your functions. So it doesn't matter which number you choose, so just choose a nice one. Okay. Now notice that f at 0 is going to be equal to 1, whereas g 0 is going to be equal to 7. Okay. Well, what does that tell us? That tells us that function g should be the one that's on top then, because it gives a higher value at 0. And f should be the ones on the bottom because it gives a smaller value at 0, okay? All right, so then the general method is pick a number in between your x values, plug it into both functions. The one that returns the larger value was the one that was on top, all right? Now, of course, just having a rough idea about what it looks like will also help. From what I can tell, most of your problems are probably going to be fairly simple. It's probably going to involve a parabola and a line. So here, this is a parabola because it's quadratic. It'll open upwards because the coefficient of x squared is positive. So you know that f of x will look like this. Then you know that g of x is a line and it has a negative slope. So you know that it slopes downwards. So you can kind of get a rough idea. It looks something like this, and g would be the one that's on top. So without graphing it too accurately, just by recognizing f is the parabola, g is a line sloping downwards, that's kind of enough to also figure out which one was on top and which one was on bottom. All right, but once we have all of that, what we can now do is just set up the integral to calculate the area. So we're going to integrate from -2 to 3. And then we're going to do the top function, which is g of x, minus the bottom function, which is f of x, which is the quadratic, like that. Yeah, so we'll take a look at that when we get to problem number 4. All right, so then at this point, you would just work this out to calculate the area. All right, Would you guys be all right if I left the problem at that and instead went on to problem number 3? Or would you like to see me work out the definite integral there as well? All right, yeah. So let's go to problem 3 and see how to set that one up. Okay. All right, so now problem number 3. Now so not only does it give us bounded by 2 functions, but it also gives us bounds on x as well. Okay. So still what we're going to do, if they give us a bound by 2 functions, then you do want to still check where those 2 functions are going to intersect each other. So even though they gave us the bounds on x already, we still want to check where they intersect because there's a possibility that they might switch between which function is on top and which one is on bottom. They might switch within this interval. So that's why we first want to check where they're going to intersect, all right? So again, to do that, just set the 2 functions equal to each other. Here, let's add x squared over to this side. Then minus the 5 over. Okay. All right, and then here, let's see if we can factor this. So I'm just going to try and just do it by guessing is what I'm going to do. So to get minus 5, it's got to be plus 1 and minus 5. Okay, so it looks like if I do plus and minus 5, that would do it. Okay, so that's 2x squared plus 2x minus 5x to get minus 3x, and then minus 5, okay? Great. But what does that tell us? We see that they're going to intersect when x is negative 1. And then setting this equal to 0 and solving for x, get x is 5 over 2 for the other place where they're going to intersect, all right? Okay, now, so I'll draw just like a really rough picture, right? So let's say like here's negative 1, here's 5 over 2. So they intersect at these points. I don't really care too much what they look like, so I'll just draw something really generic. All right. Now, however, for the purpose of the problem, we only want the area between 0 and 1. Okay. So here we can kind of see that we don't need to worry about the functions intersecting in this interval and changing which one was on top and which one was on bottom. You're just going to have one function consistently on top and one function consistently on the bottom, all right? So then figuring out which of the functions was on the top and which one was on the bottom. Okay, so one thing that you can do is, in this case, just you can plug in either 0 or 1 or any number in between into the functions to see which one gave you the larger and which one gave you the smaller value. All right. So I guess 0 is a nice number, so let's plug 0 into both f and g. So f of 0 is 5, g of 0 is 0. So that tells us then that f must have been on top and g must have been on the bottom. So we're going to calculate this area by doing the integral from 0 to 1 of f of x and then minus g of x. Okay. So you evaluate this definite integral, and that will give you the area. All right, so then I guess let's also check number 4 then. So we'll leave the definite integral unevaluated, but of course to get the area, you should finish evaluating it, okay? Okay, so finally, let's take a look at number 4. So it's similar to number 3, bounded by two functions. And they also give us the bounds in x already. So again, what we're going to do is start by looking at where the two functions intersect each other. Okay, so set f of x equal to g of x. And let's move the 3x over. Move the 4 over as well. Here we'll try to factor that. So it looks like x minus 5 and x plus 2. So therefore they intersect at x equals negative 2 and x equals 5, okay? And then I'm just going to draw a super rough picture. So we know they're intersecting at negative 2 and 5. I don't care too much about what the functions look like, so again, I'll just draw something generic. They intersect like this. Okay, but now we notice that we're interested in the area between 2 and 7. So now let's mark 2 and 7 in the picture. All right, so what's happening is if I extend this picture past 7, or past 5 to 7, we get something that looks like this. Okay? So between 2 and 7 is all I care about, so maybe I'll just get rid of that, ignore it now. And so what we see is whatever function starts on top, it actually ends up on the bottom past 5. And then likewise, whichever function started on the bottom ends up being the one that's on top once we pass the value of 5. Okay? So what we'll do is we'll calculate each of these areas separately, and then at the end we'll add them together to get the total area between 2 and 7. Okay? And so then figuring out which of them is on top. Okay. So first we want to figure out which one's on top between 2 and 5. So pick a number between 2 and 5. I guess we can just pick go to work, but maybe we can also just pick 3. Doesn't really matter. Okay, so I'll pick the number 3 between 2 and 5. Just plug them into F and G. Okay, so let's see here. F of 3 is going to be 9 minus 6, so it'd be 3. G of 3 would be 9 plus 4, which is 13. Okay. So therefore, we see that G is definitely the one that's on top between 2 and 5. So then we can calculate area A1 by doing the integral from 2 to 5. And we're going to have G of x minus f of x. Okay, so that gets us area A1. And then next, if we focus on what's going on between 5 and 7, so pick a number between 5 and 7. So we'll pick 6. And just plug it into, again, both functions to see which one will come out on top. So this was f of x. If we plug in 6 for x, we're going to get 30. Here's g of x, so plug in 6 for x, and you get 22. So now, as you can see, f is now the one on top. So area A2, you'll do the integral from 5 to 7 of this time f of x minus g of x. And then finally, once you evaluate the two definite integrals here, add them together to get the total area. Yeah, so it's likely the case that once you know G was on top in the first area, therefore the F would be on top in the second area. In theory, it's possible that that won't be the case. Because in theory, you could have a picture like this. Where whichever function was on the bottom after the intersect remains on the bottom. Now, I guess probably you're not going to see that, but there's always a possibility. So if you want to be extra safe, yeah, always double check which one's on top in the second area as well. All right. All right, now in that case, I didn't quite get to volume or average value. I'll just quickly mention the formulas for it at least. Then I'll go ahead and end the review at that. So then just real quickly for the volume, the formula is going to be pi times the integral from a to b, whatever your function is, squared dx. And then just remember that for average value, the formula was 1 over b minus a, and then times the integral from a to b of your function. All right. So then at this point, I'm going to go ahead and stop the recording and end the review, okay?